Usually when we talk about a medical diagnosis, there's um, this comforting expectation of precision. It feels almost like engineering,
Oh,
right?
absolutely. It's very black and white.
Yeah, exactly. Like you break your arm, the X-ray shows this jagged white line on a black background, and the doctor just points at it and says, there it is, broken.
Right. And the binary nature of that is deeply reassuring to us. I mean, we've basically built our entire modern civilization on this premise that problems can be isolated, categorized, and then treated linearly.
But then you step into the world of planetary science,
Hmm.
and you very quickly realize that the X-ray machine itself is, well, it's giving us a completely false sense of security.
Yeah, it really is.
Because when we look at Earth's diagnostic landscape today, we're basically using the wrong tools to measure the wrong disease.
That's a great way to put it.
So welcome to today's deep dive. We are unpacking a massive stack of documents from the KOSMOS Institute of Systems Theory, specifically a framework authored by Clinton Alden. And I got to tell you, it demands a total paradigm shift.
It really does. It flips everything you thought you knew right on its head.
We're going to explore why treating the climate crisis as a temperature problem is a fundamental and honestly maybe fatal mistake. Because it's not a temperature problem, it is a complexity problem.
Right, which fundamentally challenges all the metrics that policy leaders have been relying on for, gosh, decades now.
Decades, yeah.
So in this deep dive, we're going to translate some highly technical systems theory, specifically the 7ES framework and its focus on modal dynamics, into clear, actionable insights.
Because you need to know how the mechanics of planetary survival actually work.
Exactly. The core thesis we're looking at is why Earth systems literally lose the mathematical capacity to stabilize within human timeframes, and this happens long before the temperature ever actually peaks.
Okay, so to fix a problem, we first have to understand why our current predictive tools are failing us so badly. I mean, we rely heavily on these massive supercomputer models, right? The CMIP6 models.
So that's the CMIP6 models. We rely on them to tell us what the climate is going to do next.
Right. But from a systems theory perspective, these models are just dangerously blind. They focus almost entirely on lag indicators.
And that is the critical flaw right there. Look, current models are incredibly sophisticated at tracking, temperature anomalies or atmospheric greenhouse gas concentrations, sea level rise, all of that.
But they're missing the big picture.
Completely. Because measuring those metrics is just measuring the physical consequences. It's the symptoms of an energy imbalance. It tells you how much heat is trapped, but it gives you almost zero data on the planet's underlying structural capacity to actually, process or survive that heat.
It's like, it's like staring at your car's speedometer to predict when the engine is going to explode.
Oh, that's a perfect analogy.
Right. The speed you're traveling isn't the actual problem. The structural integrity of the engine block under that stress is what matters. But, I mean, I have to push back a little here. Are climate scientists really that blind? Or are we just, obsessing over temperature because it's a number we can easily just slap on a graph?
Well, it is deeply tied to how we construct mathematical models. Like you said, temperature is very easily quantifiable.
Right. It's a simple number.
Exactly. But systemic complexity, that requires mapping these massive cascading relationships across fractal scales. I mean, all the way from soil microbes up to the jet stream.
Which is wildly complicated.
Exactly. And this is where Alden introduces the concept of modal dynamics. The models fail because they lack what the paper calls requisite modal variety.
Okay, let's unpack that.
Basically, they don't mathematically separate dynamic modes from structural modes.
Right, and modal variety sounds incredibly abstract, so let's define that for the listener. We're really just talking about the difference between the fast things humans are doing versus this slow, ambient background operations of the planet, right?
Exactly. Think of a mode as just a distinct pattern of behavior in a system. So dynamic modes are these fast, high energy costly changes. These are the human inputs.
Like industrial emissions and that sort of thing.
Right. Massive land use changes, emissions, nitrogen runoff from agriculture. Whereas structural modes are the slow, persistent, natural background systems.
Things that have been here forever.
Right, like orbital cycles, the deep ocean currents, the slow weathering of rock. The problem is current climate models tend to mash all these things together.
Oh, I see.
They assume that if a dynamic mode pushes the system out of balance, the system will just smoothly, linearly return to a new equilibrium. They assume linear recovery.
But they completely ignore the structural shear that happens when you force a really fast energetic change onto a slow structural foundation.
Precisely.
So if our primary models can't track that shear, we clearly need a different diagnostic framework. Which leads us to a rule from 1950s cybernetics that this Cosmos Institute paper applies to planetary health, which is just fascinating.
Ashby's law of requisite variety.
Yes,
Yeah.
Ashby's law. Okay, let's unpack this one because the law states simply that only variety can destroy variety.
It sounds like a riddle, but it's brilliant.
It is. So in plain terms, if a system faces, say, 100 unique environmental threats, it needs at least 100 distinct internal regulatory responses to maintain its stability.
It's essentially the mathematical definition of an immune system.
Right, so applying that biological analogy to planetary physics kind of reveals the true scale of what we're facing. Historically, Earth had this massive, robust immune system of biological diversity, complex food webs, chemical buffers, all of that.
And in systems theory, that is its internal regulatory variety.
Okay, regulatory variety, got it.
And it could process the environmental variety, the natural shocks, like huge volcanic eruptions or shifts in solar radiation, because it had enough internal pathways to basically dissipate that energy.
But human activity over the last century has acted like, well, like a million novel viruses attacking that immune system all at once.
That is exactly what the data shows.
Because we aren't just warming the air. We are introducing completely new disturbance vectors that the planet literally has no historical defenses for.
And the Cosmos data quantifies this mismatch, and the numbers are just staggering. Since 1950, humans have introduced environmental disturbances that operate 3 to 6 orders of magnitude beyond Earth's natural regulatory capacity.
Wait, really? 6 orders of magnitude?
Yes. For example, we have synthesized 15,000 distinct PFAS compounds.
The forever chemicals.
Right. These have molecular bonds that simply do not exist in nature. The planet doesn't know how to break them down. We've flooded the biosphere with microplastics that present just infinite size and shape combinations to marine life.
Oh, wow.
And we are injecting carbon dioxide into the atmosphere roughly 100 times faster than the most extreme natural geological processes in Earth's history.
So we are just completely saturating the planet's immune system. We're forcing it to deal with this astronomical volume of novel disturbance states, and at the exact same time, we're bulldozing the biodiversity and soil health that the planet would normally use to regulate itself.
Exactly, you were squeezing it from both ends.
Yeah.
And that simultaneous pressure creates what the framework calls the regulatory capacity deficit.
Okay, regulatory capacity deficit. What does that mean in numbers?
Well, sometime between 1970 and 2000, we crossed a terrifying mathematical threshold. The Earth's dynamic regulatory compliance, which they represent mathematically as a subdilit, dropped below 1.0.
With 1.0 being the baseline where the internal defenses perfectly match the external disturbances, right?
Correct.
So, where are we now?
The current compliance metric sits at 0.92.
Okay, but that still feels a little abstract to me. Like, how do you actually quantify variety mathematically to arrive at a 0.92 deficit? Because we measure carbon in gigatons, right? But how do we measure missing complexity?
It's a great question. You measure it using information theory, specifically something called Shannon entropy. Yeah, it calculates the number of distinct states a system can occupy. So imagine a fraction. The numerator is the volume of novel disturbances, the plastics, the forever chemicals, the massive heat flux.
Right.
The denominator is the available biological and chemical regulatory pathways.
Oh, I see.
So because the numerator has expanded exponentially, and we've actively destroyed the denominator by wiping out ecosystems, the math yields a deficit. The system mathematically lacks the pathways to process the stress.
Wow. Which, I mean, that brings up the most common counterargument you always hear when people talk about planetary collapse.
Yeah.
People always say, well, the Earth has survived way worse.
Right. The planet has been through this before.
Exactly. And it's true. I mean, it survived the KT extinction event. If the planet can literally take a direct hit from a dinosaur-killing asteroid, surely it can process some microplastics and a few degrees of warming, right?
Well, here's the thing. The planet absolutely will survive. The Earth absorbed an asteroid impact, delivering 10 to the 23rd joules of kinetic energy.
Which is mind-boggling.
It is. But viewing that as a comforting fact falls into what the Cosmos framework identifies as the timescale trap.
The timescale trap.
Yes, the planet survived, sure, but the recovery of full ecosystem complexity and regulatory capacity after that asteroid impact, that took roughly 10 million years.
Oh, yeah. And here's where it gets really interesting, because there's this brutal mismatch. Human agricultural and industrial civilization we require incredibly specific, stable, Holocene-like conditions to survive.
We absolutely do.
Like, we need predictable monsoon seasons to grow rice. We need stable coastlines for all our global shipping infrastructure. Our viability window as a civilization isn't measured in millions of years. It operates on timescales of decades to maybe millennia.
Right. Mathematically, that's 10 to the power of 1 to 10 to the power of 4 years.
Right.
If we connect this to the bigger picture, the timescale impossibility becomes just glaring. There is a 4 to 6 order of magnitude difference between Earth's natural structural recovery time and human civilization's survival time frame.
That is terrifying when you put it like that.
It is. We are forcing these massive dynamic changes onto the system today. If we push Earth past its tipping points, past its capacity to regulate, the planet will eventually establish a new equilibrium. It will build new structural modes. But that process will take millions of years, and human civilization will have been extinct for millions of years before that stability returns.
The author puts it in such a chilling way in the paper. They say, we are basically conducting a slow-motion asteroid impact on ourselves.
Yes, a continuous accumulating impact. Think about it. The dinosaur asteroid was an instantaneous shock, and it was followed immediately by the start of a 10 million year recovery.
Right.
Our shock is ongoing, which means the planetary recovery clock hasn't even started ticking yet.
Man. Okay, so if the temperature models are lagging indicators, and we know this timescale trap is just sitting there waiting for us, how do we actually measure our proximity to the edge before we fall off?
We need a leading indicator.
Right. We need to know when that structural failure is going to cascade.
And the KOSMOS Institute addresses this by introducing an alternative to traditional metrics. They call it the Climate Viability Score, or P-sub-viability.
The viability score.
Exactly. Instead of just looking at active feedback, which is, how the system violently reacts to warming, like permafrost thawing and suddenly releasing huge burns of methane, this metric measures passive feedback.
Which means looking at a system's ability to just persist in its historical state, right? Like the mere fact that a forest is still functioning as a forest rather than actively dying is the true measure of its structural integrity.
That's exactly it.
But how do you convert passive existence into a hard mathematical score? So what does this all mean for the actual physical parts of the planet? What are we looking at to get this score?
So you measure the variance within the safe historical operating envelopes of major planetary subsystems. The framework actually monitors 7 critical ones.
Okay, 7 subsystems, like what?
Well, take the AMC, the Atlantic Meridional Overturning Circulation.
Big ocean current.
Right. Historically, this massive ocean current flows at a rate of 15 to 25 Sverdrups, continuously transporting heat from the equator all the way up toward the Arctic.
And for context, a Sverdrup is just a massive volume of water, right? Like 1 million cubic meters per second.
Yes, it's an almost unfathomable amount of water moving. But that flow rate is slowing down. It's currently dropping below 17 Sverdrups. It is brushing right against the edge of its historical viability envelope.
Wow.
And the framework also monitors things like Arctic sea ice and the Amazon rainforest, which is nearing a 20 to 25% deforestation tipping point where it would transition into a savanna.
And obviously those subsystems don't exist in isolation.
Not at all.
Like if the AMOC slows down, it fundamentally alters the thermal gradients in the ocean. And that heat buildup in the South Atlantic shifts the global rain belt further south, which literally starves the northern Amazon basin of rainfall.
Yes. That dynamic coupling is exactly what the viability score captures. So when you aggregate the variance of all 7 subsystems, the current overall viability score is 0.76.
76%. I mean, on a math test, that's a passing grade. But for planetary life support, it basically means we've already lost a quarter of our structural persistence.
Exactly. It places us firmly in the caution zone. We have lost structural redundancy, but the systems are technically still functioning.
For now.
For now, the real warning lies in the rate of decay. The score is declining by 0.05 to 0.10 per decade.
Okay, so projecting that forward, we cross 0.5 50% by mid-century. What happens at 0.5?
That 0.5 threshold represents the red zone. It is the mathematical tipping point where passive persistence collapses.
The tipping cascades.
Yes, the subsystems can no longer absorb the dynamic stress, and they structurally transition into active, self-reinforcing destruction modes.
Oh, man.
The Amazon transitions into a savanna, meaning it stops producing its own rain. The AMOC collapses entirely. The structural shear we discussed earlier finally breaks the system. unstoppable tipping points become highly probable.
Which makes this, like, the absolute most critical moment for any policy leaders who are focused on long-term climate risk.
Mm.
We have a very clear metric and a frankly terrifying deadline of mid-century.
Yes, the clock is ticking loudly.
So how do we fix it? How do we get our compliance metric back to 1.0 before our viability score drops to 0.5? What do the people in charge actually need to do?
Well, the Cosmos playbook is draconian, but mathematically it's necessary. To restore Ashby's law of requisite variety, the absolute priority is you must aggressively stop adding new dynamic disturbances.
Right. You have to shrink the numerator in that fraction you mentioned earlier.
Exactly. You must reduce environmental variety. This means an emergency 50% phase out of fossil fuels within 5 years.
5 years. Wow.
It also requires an immediate global moratorium on novel chemical synthesis and plastics.
Because every single new chemical compound is a brand new disturbance vector the planet has to figure out how to process.
Exactly. And furthermore, it requires massive global rewilding, strictly protecting 50% of all degraded terrestrial and marine ecosystems immediately. You have to preserve and rebuild the biological complexity that serves as the planet's structural buffer.
Okay, I want to push back on this just a bit from an economic perspective because, let's be real, policy leaders rarely choose the hardest, most draconian path if there's a cheaper technological alternative out there.
That's certainly historically true, yes.
But wait, what about geoengineering? Specifically, solar radiation management, or SRM?
Yeah.
Because economically, it is incredibly cheap to just spray reflective aerosol particles into the stratosphere to bounce the sun's rays back into space, right?
Yeah.
And it lowers the temperature almost immediately.
Yeah.
Can't we just do that to buy ourselves time?
This raises an important question, but evaluating solar radiation management through the strict lens of Ashby's law reveals exactly why it is a catastrophic trap.
Really?
Yes, SRM introduces a massive new dynamic mode to the system. You are attempting to suppress the volatility of a complex system by stacking a brand new, highly complex disturbance right on top of it.
Oh, I see. So you actually increase the environmental variety instead of reducing it.
You increase it exponentially. And it does absolutely nothing to address the underlying variety deficit. Because underneath that artificial thermal shield you've built, carbon dioxide concentrations keep rising.
Right.
Ocean acidification continues to accelerate, which dissolves the calcium carbonate shells of marine phytoplankton. And they form the base of the entire oceanic food web.
So you're just masking the lag indicator of heat,
Yeah.
while the actual structural capacity of the biosphere just continues to rot away underneath.
Precisely. It is dynamically dangerous. And the shear between the dynamic and structural modes just builds up like pressure in a fault line.
And I guess if geopolitics or economics ever force us to stop spraying those aerosols, the underlying variety deficit is still there, and the heat just snaps back in this termination shock that the planet's depleted immune system has absolutely no chance of surviving.
Exactly. It's a false fix. The framework makes it very clear that any technological intervention must physically remove variety from the system to be effective.
Okay, so what's the real solution then?
This is why the paper heavily prioritizes large-scale carbon dioxide removal, or CDR.
Ah, because mechanically pulling carbon out of the atmosphere actually subtracts a disturbance vector.
Yes. By physically removing the excess carbon, you are directly lowering the environmental stress. CDR is the only technological intervention that actually reduces environmental variety.
So it restores planetary self-regulation.
Exactly. It actively restores the planet's capacity for self-regulation and improves our Ashby compliance without introducing some crazy new uncoupled dynamic mode. It addresses the actual disease rather than just masking the symptom.
Okay, so to summarize this massive paradigm shift we've just been on,
Yeah.
we have to stop treating the climate crisis as just a rising line on a thermometer.
Yes, the heat is a lag indicator.
Right. The true crisis is this systemic loss of structural capacity to protect us. We have to measure the disease, the variety deficit, because by the time the temperature models show the final spike, the structural foundation of the planet will have already fractured way beyond our ability to repair it on any human timescale.
Because human civilization requires planetary stability measured in decades, not geologic epochs. Recognizing that timescale limitation just fundamentally changes how we must view risk and policy intervention.
Wow. Okay, I want to leave you, the listener, with a final unexamined thought to ponder, and I want to step away from the climate for a moment to do it.
Oh, interesting.
Because if Ashby's law of requisite variety applies so brutally and mathematically to Earth's ecosystems, we really have to ask where else in our modern human world we're dangerously violating it.
That's a great point.
I mean, think about our hyper-optimized global supply chains, or our algorithmic financial markets, or our centralized food distribution networks.
Oh, absolutely.
For decades, we have aggressively stripped the regulatory variety, the buffers, the redundancies, the natural inefficiencies out of human civilization entirely in the name of efficiency and maximizing quarterly profit.
We've removed all our internal buffers.
Exactly. Are we systematically blindly racing toward a social or economic structural failure that we have absolutely no models to predict simply because we're only looking at the lag indicators of GDP and stock prices?
We've been staring at the X-ray, totally ignoring the actual health of the system.
Exactly. It's wild to think about. Well, thank you so much for taking this deep dive into systems theory with us today. Stay curious, keep questioning the models, and we'll catch you next time.